Welcome back, everybody. In the last video, I encouraged you to ponder the question, does any infinite series necessarily diverge? Most people instinctively say yes, that if you continue to add more and more stuff, that the sum has to be infinity, so an infinite series must diverge. In this video, I'll walk you through a couple of examples. Let's see if we can refine what our gut instinct tells us. Let's investigate the following series. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus 1 over 64 plus ... Does this sum add up to infinity? This one has a very nice geometric interpretation. Suppose you have a 1 by 1 square. What is its area? Multiplying the length and width, 1 times 1 equals 1. So the area of the square is 1. Now suppose we cut the square vertically down the middle, so the left rectangle has half the area of the whole square, so 1/2. The remaining right rectangle also has an area of 1/2, but let's cut it again, horizontally this time. The top square will have half the remaining area, so 1/4. Continuing in this way, each half of the remaining unshaded part will be half as big as the previous. Hopefully you can see that these area values are matching up with the terms of the series we set out to explore. So what do you think is the sum of all these numbers? It should be represented by the sum of all of the areas in the image. Notice that the amount we add each time is only half as big as what remains unshaded. So we'll never fill the original square. However, if we could continue this forever, in theory, we'd reach a sum of 1. Therefore, this sum of this series isn't infinity because it converges to 1. This is usually the part where people get uncomfortable, and I can't blame them. That is why I made this video, to help this become more comfortable. It feels counterintuitive that you could continue to add forever and the sum could stabilize. But think for a moment. Suppose you had some existing quantity. Can you think of a number you can add to it that doesn't change the original value? 0 is called the additive identity because when you add 0 to any number, that number's value or identity is preserved. Here's a silly example. 1 plus 2 plus 3 plus 4 plus 5 plus 0 plus 0 plus 0 plus ... Now this is not something you're likely to encounter in a math class. But the point is that if all I'm ever adding at the end is zeros, the infinite sum is no different than the sum of the first 5 terms, and therefore converges. Again, this is not how things will happen in meaningful problems. You won't be seeing terms that are actually a string of zeros at the end. But what if the terms were really close to 0? Or close enough that their contribution to the sum becomes insignificant? Think back to the filled out square in that last example and notice that the amounts we were adding towards the end were so tiny that they couldn't overflow the square, and that is why the sum converged. Let's take a look at another example. How about 1/10 plus 1/100th plus 1,000th plus 1/10,000th plus ... This time a square won't help as much. Let's instead look at the decimal values of each term. Since 1/10 is 0.1 and 1/100th is 0.01 and 1/1000th is 0.001 and 1/10,000th is 0.0001, when we add these vertically, you'll see that none of the ones in any decimal place interfere with any other place value. And the sum is 0.1111. If we continued adding all the terms in this infinite series, we'd get 0.1 repeating. And if you watched my previous videos about repeating decimals, you'd know that this value equals 1/9. That is probably not what your intuition thought this sum would come out to be. But this is a good time to talk about repeating decimals again. If you were already aware of numbers with infinite decimals, whether they were repeating like 0.333 repeating, or non-repeating irrationals like pi, which is approximately 3.14159, and then more stuff with no pattern, then you already have seen numbers that are infinitely long, but not infinitely large. That should give you a little bit of comfort within this crazy idea. Okay, so where are we now? We've seen that if the sequence diverges, the series also diverges. But what if the sequence converges? Would it matter what it converges to? Let's change our silly example from before. Before, we were looking at 1 plus 2 plus 3 plus 4 plus 5 plus 0 plus 0 plus 0 plus 0. This time, let's look at 1 plus 2 plus 3 plus 4 plus 5 plus 5 plus 5 plus 5 and continue to add 5s. Now, the sequence itself converges to 5. But anytime you add 5 to anything, the value will not remain the same because 5 isn't the additive identity. This means that the sequence terms must approach 0 in order for the series to converge. But wait, there's more. We just saw that the limit of the sequence being 0 is definitely a necessary condition for the series to converge. But is it sufficient? Meaning, if the limit of the sequence is 0, does that guarantee that the series converges? Let's see. Let's look at one last example. A very famous and important series is called the harmonic series. It goes 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... This one looks very similar to the other series we saw, starting with 1/2, followed by decreasing fractions. Let's take a look at the decimal values of just the first 9 fractions in this series and see what the partial sum is. I encourage you to pause the video and grab a calculator to add those 9 fractions yourself to make sure you also get 1.929. First, notice that all these values that are less than 1 add up to more than 1. Now let's inspect the numbers in the tenths place. Notice that the total has a 9 in the tenths place, and this suggests that the sum of the values in the tenths place is 19. However, if you check, the sum is actually 17. So where did the extra 2 come from? Let's look at the hundredths place values. Those add up to 21, which means the 2 spilled over to the tens place. But in the hundredths place, the total is also not 1, it's 2, suggesting that there was spillover from the thousandths place too. So what we're seeing is that very slowly, the sum of the values in any column is not terribly small and keep spilling over to the next place value to the left. Also remember that we only used 9 fractions, not infinite fractions. So the actual sum is larger than what we got. This suggests that the infinite harmonic series diverges to infinity. Let me remind you that this isn't a proof of anything. Many other people have posted videos of how to prove rigorously that the harmonic series diverges, and I encourage you to watch those. However, my purpose in making this video is to help you develop your intuition about infinite series and clear up some common misconceptions about how they behave. Let's summarize what we've observed in a flowchart. What does the behavior of the sequence tell us about the behavior of the series? First, if the sequence diverges, like in the example 1 plus 2 plus 3 plus 4 plus 5, etc., the series must diverge. But if the sequence converges, The convergence or divergence of the series depends on the limit of the sequence. If the sequence converges to a non-zero value, like the example with the repeating 5s, then the series diverges. But if the sequence converges to 0, then we have to consider how fast the values are approaching 0. If the values approach 0 too slowly, like in the harmonic series, then the sum won't stabilize and the series diverges. If the values approach 0 quickly enough, like in the sum of the powers of 1/2, then the series will converge. Now you may notice a giant problem right here. If a sequence approaches 0, how do you determine what is approaching 0 too slow or quick enough? This feels very subjective and doesn't have a solid conclusion. Thankfully, there are other tools we can use to determine convergence or divergence, but we'll cover those in another video. But the chart shows us something very helpful. It shows us that if the sequence is not approaching 0, then the series has to diverge. This concept is often called the nth term test for divergence. It says that if the limit of the sequence is not 0, then the series diverges. I want to make sure the message gets through, so I'll say it again. This way of thinking cannot be used to determine convergence, only divergence. The logic is that if you are not ultimately adding values that are basically 0, there is no way that the sum is going to settle down. I hope you found these examples and discussions helpful. I have taught the series topic in calculus classes for over 20 years, and this is one of the concepts that causes students the most confusion. That is why I specifically made this video without intense sigma notation or algebraic proofs. The more you feel what is going on here numerically and geometrically, the better you'll be able to grasp the problems you'll see in class. If it doesn't all make sense the first time you hear this, you are not alone, and watching this video more than once could help. Please leave comments on the video or reach out to me by email if you have additional questions. Thank you so much for watching. I hope you enjoyed this video. See you next time.